Hello, everyone. Welcome to today's conversation, which is gonna straddle the arenas of quantum mechanics, general relativity, some cosmology, probably some black holes, and certainly the idea of holography will no doubt make an appearance. And I'm so pleased that our guest today is someone who has contributed so profoundly to our understanding of so many of the subjects that I just rattled off. He's a Chancellor Chair in Physics at the University of California, Berkeley, and a friend of mine over the course of many decades. It's Raphael Bousso. So welcome, Raphael. Thanks for joining us.
Thank you for having me, Brian. It's great to be back.
Absolutely. And by back, of course, you mean you have been in World Science Festival programs many times.
I'm an alumnus.
You are.
I'm a very proud alumnus.
Thank you. So I wanted to begin in quantum mechanics. So we're now in the 100th anniversary year of the subject. Do you see any evidence at all that there are any cracks in quantum mechanics?
It's funny that you asked that. I wrote a short essay maybe 10, 15 years ago expressing my puzzlement about the fact that we don't have any evidence at all that quantum mechanics needs to be revised, changed, extended. That's not to say that I know for sure that it's the final word, but it's very unusual that we have a framework in physics that doesn't show some cracks, that doesn't show signs of its own demise.
Yeah.
One of our most successful theories, general relativity, which describes gravity, how the apple falls, how the moon and the planets move, and how the universe expands. It's incredibly successful. It can do all these wonderful things to great accuracy, but we also are quite sure that it's not the final word. We've already seen some examples how space and time can emerge from deeper, more fundamental objects. And we also know that the theory sort of predicts things called singularities. It predicts infinities that make no sense. And so that's an example of where we have a great theory, but we also know it's not the last word. And really, all of physics, the history of physics, is a history of finding better and better theories, none of which are supposed to be the last word. They're just explaining more things more accurately from fewer ingredients. Quantum mechanics, it's got no crack in the armor.
Yeah.
It's even when we combine it with gravity to the extent that we've succeeded in doing that, it was not by modifying quantum mechanics. The theories that we have that are sort of candidates or partly sort of quantum theories of gravity are fully quantum mechanical.
So we'll get to some of those mergers or attempted mergers between gravity and quantum mechanics in just a little while. But on quantum mechanics itself, Niels Bohr, one of the founding fathers of the subject, liked to say that the only role of physics, and therefore the only role of quantum mechanics, is to explain the readouts that we find in pieces of equipment. And if we can do that, explain the measurements, why you got 2.7 when you measured that, or 3.6 when you measured that, then we're done. Is that your view of what physics is ultimately about?
I love physics because it is an interplay between this sort of hard-nosed attitude. Well, yes, physical theories are about explaining the measurements we make. I don't have a lot of patience for people debating what's real. It doesn't matter. We haven't made any progress at all by debating what's real. What we've made progress by is making very accurate measurements and demanding of our theories that they explain them. And also by demanding of our theories that they be as simple as possible while explaining as much as possible. I think a great example is, the famous perihelion precession of Mercury.
Yeah.
It's mind-numbing to think how hard and tedious it must have been for astronomers to realize that one of these planets in the solar system is off by some infinitesimal amount per century compared to the predictions of Newtonian gravity. And yet, that tedious work, and really I don't care where Mercury is personally, but that tedious work is the chink in the armor that says Newton has to go down. We need something different. oh, it turns out space and time are dynamical. Gravity isn't even a force. And that's the other side of it. It's this mind-blowing conceptual stuff that's tied to the tedious measuring data points stuff. That they go hand in hand. They cannot be separated from one another. And quantum mechanics has certainly given us a lot of both. It's conceptually mind-blowing, and it also explains the data.
Yeah.
And so I feel, and I'm probably a little bit of an outlier. For example, I don't understand why people feel it needs an interpretation. It's like a little old lady you have to help across the road or something. No, it's the most powerful theory we've ever discovered. It's doing fine without your interpretation.
Well, let me come to my take on that in just a moment. But certainly your description of general relativity and how to explain the precession of the perihelion of Mercury, we had to introduce these wild new conceptual ideas of the dynamism of space and time, and ultimately they come together to explain the observations. When it comes to quantum mechanics, do you have a similar sense in your mind or in your intuition about what it's telling us about the nature of reality?
I will concede that I think it's not as neat as it is with general relativity and other physical theories that came before it, where it's very clear cut. We're sort of, well, maybe we were not born with an intuition for four-dimensional curved space-time. I was about to say we were. That's really professional deformation. But it's still, the concepts are not wildly separated from mathematically related ones for which we do have a good intuition. I'll put it that way. Quantum mechanics is fundamentally different. I think it sort of leaves us at the point where, you get to add states of a system. You get to add a state where you're sitting in this chair and a state where I'm sitting in this chair and you're in this one. And that is something that makes perfectly good sense in the theory. It's an allowed state. There's fairly straightforward explanations for why those states don't last for very long, why we don't see them. It's an interesting question that was gotten completely wrong in the early days of quantum mechanics. But the fact remains that this is an allowed state, and it's very hard to sort of, wrap your mind around it. And another fact that I think makes it hard for us to process quantum mechanics is that it requires us to be willing to say that what seems like one system can have very different descriptions from the point of view of observers with different levels of knowledge about it. So for example, if there was a spider that has surrounded the galaxy with an impenetrable net, then all the different outcomes of quantum experiments that we do would still all be there for that spider, and it would just say that there's a superposition. And this conflicts in no way with the fact that we see definite outcomes. We don't see the whole galaxy. We lose a lot of information that explains this fact. But it's something that's very hard to wrap your head around, to sort of accept. And I feel like a lot of the philosophical debates around quantum mechanics are centered on this very human discomfort.
And so the aspect of quantum mechanics, of course, that you're highlighting there, I guess in technical terms, we call it superposition.
Right.
But in the end of the day, if we apply it to a particle like an electron, the theory basically says if the electron could be here, that's an allowed place for it. And if it could be there, that's an allowed place. Then there is this somewhat unfamiliar state of the electron where it's in a combination of here and there at the same time. And as you're saying, it's very hard for us human beings to fully grasp what that really means. But then you're also making an important point, and I'd like to dig down a little bit deeper, because I'm not sure how many in our audience are familiar with the fact that we do have a reasonable understanding of why it is that we human beings don't directly experience the particle here and there, or the cat both dead and alive, or whatever weird combination quantum mechanics allows.
Yes. I think this is actually a beautiful story. It's a little bit frustrating how long it took people to appreciate this story. It's called Decoherence.
And just to say, I took quantum mechanics in the 1980s, with a Nobel laureate, Norman Ramsey, the word decoherence didn't make an appearance in my course on quantum mechanics.
I took it in the 90s, not from a Nobel laureate, I wish. But I was furious when I learned about decoherence as a postdoc. Not even like in my first couple of years as a postdoc. Like after I got a PhD and I was already a postdoc for a couple of years, and you will never guess who explained it to me. Nima, our country met. I was, somehow the topic came to this whole thing about, Schrödinger's cat and the usual story. Yeah. And Nima was like, oh, why are you worried about that? And I'm still,
But we should say Nima could explain almost any issue that any of us have with any part of physics.
This changed my life. Yes. No, it's a very beautiful story because what it has to do with is something that's, again, counter to our classical training, our classical intuition. When light falls on this chair, and we analyze the chair's motion, we don't care about that. When the air molecules bounce off of it, we don't care about that. We know this is a heavy chair. There's a lot of friction. It's not going to do anything. It's just going to stay there, right? But in quantum mechanics, this matters. And I think this is maybe why it was overlooked for so long. It's because the interactions of such weak interactions of an environment with a large microscopic system normally could be neglected. Physicists are sort of trained to forget about them and try to keep things simple, focus on the essentials of the problem. But if I put this chair into a state that is a state of chair is here plus the state chair is over there, and even if there's a single light particle coming down from the ceiling, then in one half of the state where the chair is here, that light particle is going to bounce off the chair and its trajectory is altered. And in the other half of the state, the light particle will continue down towards the floor and it will end up with a different trajectory or be absorbed by the floor. Now, if you don't keep track of that light particle, then there's a calculation you can do about what the system now looks like to you. And it no longer looks like chair here plus there. It looks like a certain chance of chair here and a certain chance of chair there, but a 0% chance of chair here plus there. That state is no longer present for you. But if somebody had kept track of that light particle and included it in the system even afterwards, then what is called the coherence of the state would be preserved. This is what I meant when I said that how we describe a system depends on our state of knowledge. And it's just a fact. This is something we can check experimentally, not with chairs, but with the electrons or with other small systems where we have enough control to do this. Now, the key thing here is, of course, that not one particle bounces off the chair, but a gazillion light particles and a gazillion air particles and so on constantly bounce off macroscopic objects. Even if we tried to, we could not isolate something like a chair. Even if we put it in a box, it would still radiate and send out infrared light. And this explains completely why we never see chair here plus there.
Right.
So there are other things that are confusing about quantum mechanics, but this is one thing that's often emphasized as being particularly confusing, and I think it's important to understand that it is completely resolved.
And so for the young quantum students who perhaps haven't encountered this yet in their course, we can quickly say we're talking about the off-diagonal terms in the density matrix are driven to zero, so it's just the diagonal terms, and go look it up in a modern quantum textbook and you'll see exactly what you're describing. But here's my question. Does this fully satisfy you in the following sense? You're absolutely right, and any undergraduate in quantum mechanics can go through the calculations that you just described, showing that after the environmental influence, whatever it may be, is properly taken into account, you don't have these weird superpositions, but you do have the state of the chair here as one possibility, and the chair over there is another possibility. And there doesn't seem to be anything within the inherent math of quantum mechanics as traditionally formulated that tells us which of those two outcomes is the one that you will see. That still seems a radical departure from the kind of physics that at least we're used to, where Newton comes along and he tells you what outcome you're going to see. He doesn't give you a list of possibilities, even if those possibilities are ones that we can easily understand. So what gives with that aspect of quantum physics?
I'm trying to debate whether I should fight back a little bit and say, look, if you lose information in a classical theory, you also lose predictability. If I don't tell
Probably
you,
not enough for our.
if you don't tell me exactly how some bowling ball is rolling, I can't predict what's going to happen to the, what are they called, pins?
Pins, yes.
Thank you. And so it's not at that sort of hand-waving level, it's not maybe such a radical departure. The way that it works in its sort of specifics, I would agree, is quite radical. And I was saying earlier that there are other things that are confusing about quantum mechanics. I would say that this rule that emerges about how we're supposed to compute probabilities for the different outcomes, it's called the Born rule, that's probably where the rubber meets the road.
Yep.
And that's something where, some people feel that it's not satisfying to kind of put this in as an axiom. And it would be nice to derive it from the rest of quantum mechanics. There are some attempts at doing so.
Sidney Coleman did an interesting job at that years ago that for a while convinced me, and then I became less convinced when I dug yet more deeply. I don't know if you had a similar experience.
Yeah, I'll confess to a sort of residual level of confusion about, how bad it is that we have to kind of put this in as a rule for computing probabilities of different outcomes.
Right. And so do you consider the quantum measurement so-called problem to be a problem? Where do you stand on that?
Well, I would say that I think it maybe depends a little bit exactly how you define it.
Yeah.
But when we make a measurement of a small system, of a quantum system, what we're basically doing is we're turning it into something like this chair.
Yes.
We're coupling the system to an apparatus which is macroscopic, and that forces the system to behave the same way as the chair, as a big apparatus needle. Particles bounce off of it. You lose information into an environment, and so I would put that with the part of quantum mechanics that we understand quite well. It's part of decoherence. You're forcing some information into the environment, and that explains why there's a definite outcome.
Right. And so if Einstein was around today with the more modern insights into quantum mechanics, that have happened over the past 4 or 5 decades, do you think his reticence to accept it as a fundamental theory would have dissipated by now?
I almost want to say I hope not, because even though Einstein looks right now like he was kind of wrong about quantum mechanics not being an acceptable theory and needing to be replaced by something else, he put his fingers on what was weird about it. He didn't try to brush it away, paper it over, as I'm afraid Bohr, from my limited knowledge of the history, did. Bohr was like, oh, it's good for the small stuff, and then for the big stuff, we use classical mechanics and blah, 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 correspondence principle. That really didn't make any sense. It ran really counter to how physics is supposed to work. We were talking earlier about it's all about unification. It's all about having one theory for everything. And I think it may have played a role, I don't really know, but it may have played a role in why it took so long for people to understand how decoherence works. What I like about Einstein's attitude is that, it doesn't matter that much. This is actually true in a lot of examples. It doesn't matter that much whether you're right or wrong about the presumed answer, but it's the questions you ask. Mm-hmm. And the fact that he, searched for, what is the weirdest thing that I can say about what quantum mechanics is telling us? That's what you're supposed to do. Right. You push your theories to the extreme. You push them to the limit. See if you can bear the pain, and see see if they break. And then, out of that comes quantum information theory, quantum computing. All of that is really rooted in the kind of questions that Einstein was asking in the 30s. And then again, a sort of group of outsiders later on, maybe in the 70s, that that were not content with the status quo, they were also on the wrong side. They thought, oh, quantum mechanics must be wrong because, I don't know, it lets you signal faster than the speed of light. But then they discovered, or people discovered, thanks to them being annoyed about it, that no, it doesn't. Everything actually works. It's as if quantum mechanics knows about special relativity already. It respects it. And but this wouldn't have happened if people hadn't been trying to really sharpen what seemed to them like the paradoxes.
And so one of those questions that Einstein asked in the 1930s, in fact in 1935, had to do with whether quantum mechanics was a so-called complete description of reality. We don't have to go through the entire reasoning of the so-called Einstein, Podolsky, Rosen paper, but out of that, an emphasis on entanglement emerged, which is a concept that has played, again, an increasingly large role. And going back to my 1980s quantum course, entanglement didn't come up in my undergraduate class either back then. So many of these things, however familiar they are today, it really has been because the subject has matured and people have, as you said, asked deeper questions and come to grapple with things. So where do you place entanglement in the space of quantum weirdnesses?
It's maybe the single most powerful word that has come out of quantum mechanics, I would say, is entanglement. It underlies the theory of quantum computing, what makes quantum computers different from classical computers and for some purposes more powerful. And it's also a resource. You can use entanglement to send information in completely novel ways. Like, I don't have to know where you are, and still I can uniquely send you and nobody else a secret bit of information using something called quantum teleportation. But what we need for that is you need to hold in your hand half of an entangled pair of
So
particles.
maybe just quickly tell us, I'm sure most of our audience is familiar, but just what is an entangled pair?
Good. Yeah, so we can talk about bits. It keeps it really simple. So with classical bits, if I have two of them, each one of them is either 0 or 1, and if I distribute them between you and me, then each of us gets either a 0 or a 1. And if we had previously agreed that these bits mean some kind of information, for example, like 0 means it's going to rain tomorrow, and 1 it's going to be the sun shining, then we each receive one bit of information in this way. In quantum mechanics, we can, of course, also do this. We can have 0s and 1s as states, but as we've already discussed, if you can have a 0 and a 1 as quantum states, then you can also have 0 plus 1. And if I can have 2 qubits, quantum bits, in the state 0, 0, and I can also have 2 qubits in the state 1, 1, then I can have a state that is 0, 0 plus 1, 1. And people know how to prepare these states for small particles. This is not a problem at all. Now what happens if I give you one of those bits and I get one of those bits is that neither of us have actually received any information. If we go and look at the state of our bit, it's equally likely to be 0 or 1. It's completely random. And so you might think that we've received garbage. But in fact, we've received a valuable resource. These things are called entangled, if I put them in a state like that, where separately they contain no information, but together it's still 2 qubits worth of information. It's one of basically 4 states like this that you can make. But we've received a resource, and what I can use the resource for is you can go fly off into outer space, and I don't even know where you've gone. But I might want to send you a message now, 0 or 1, and to communicate to you that it's time to come home or something. And I can do that by taking my bit, the message that I want to send, and measuring it together with half of the pair that we got early on in a funny basis of states called entangled states. So I measure it in such a way that the only possible outcome of the measurement is that these 2 particles are now entangled. And then I broadcast the outcome of my measurement to the world. And nobody can use my broadcast. It turns out, if you can just calculate this using the rules of quantum mechanics, nobody can use my broadcast to infer any useful information whatsoever. It's it's a random noise for everybody else. But you, by knowing whether I sent you, which of the 4 outcomes I got, can perform an operation on your qubit and extract what I've sent you. And the reason that this works is basically that you cannot copy quantum information in quantum mechanics. More precisely, I should have said, I could do this even if my bit that I want to send you was unknown to me. Its state was completely unknown to me. I could still send it to you in this way. And now you would have this unknown bit and could do whatever you wanted with it. Maybe it's more useful to you, and I wanted to send it that way. But what you cannot do is copy an unknown quantum bit. And for this reason, this protocol that I just described is completely secure.
And so if I get that bit, then yours has changed by virtue of the process.
Exactly. I've basically destroyed both the resource and the unknown quantum bit that I had, and now it's in your hands.
Right.
And unfortunately, we can't do this again if we only had 1 pair of entangled bits to start with. And so, that's the sense in which the resource is sort of burned up.
Right.
In the
and
process.
so it's within that description, you're leveraging the fact that entanglement yields some kind of long-range connection between the 2 entangled particles. And that, again, is somewhat distinct from the way we normally think about our world. And it certainly was troubling to Einstein, whose view was, look, I'm used to a world where you do things, they have a local influence, and what happens over there is just completely distinct from what's happening over here. So do you have an intuition for how this kind of long-range quality of entanglement is achieved? Or do you just sort of, hey, this is the way the world works according to quantum mechanics, and I just accept it?
Good. A couple things. So I think one thing that often confuses people about this kind of protocol is that it seems that as soon as I've performed my measurement, instantaneously you somehow have some quantum information in your hands that I meant to send you, and you've sent it. I've sent it to you faster than the speed of light. This illustrates how important the state of knowledge of an observer actually is. Until you receive my broadcast, and my broadcast certainly isn't going to go faster than the speed of light, you still hold garbage in your hand.
Right.
The garbage turns into gold as soon as you hear 0, 1, 2, or 3 on the broadcast. Those are the 4 possible outcomes. Then you know. So I think that this really illustrates the importance of this sort of state of knowledge of the observer in how quantum mechanics works. It's fundamentally a theory of information. And I feel it should be taught that way. It should be, it has, how it works and how we need to think about it has very little to do with the hydrogen atom, as much as I respect its role in all the quantum mechanics textbooks. It doesn't really matter what carries the quantum information, whether the 0 is the hydrogen atom in a ground state and the 1 is represented by an excited state of the hydrogen atom. I mean, you could, but you could use helium instead, or you could use spins, or you could use whatever you want. The important thing is just that those are 2 states that are what are called orthogonal. They're as different from one another as they can be. And what the physical carriers are is sort of irrelevant. I think that's actually connected to the sort of Teflon properties of quantum mechanics in terms of, not being vulnerable to the inadequacies of our descriptions of sort of physical phenomena, such as quantum gravity. We don't have a full theory yet. But quantum mechanics is kind of hands-off. It doesn't really matter where the quantum information is, what represents it, and that's what keeps it a little bit apart from the rest of physics.
And so when Einstein articulated his discomfort with quantum mechanics in that 1935 paper, where entanglement was at the heart of it, there were 2 qualities of quantum mechanics that were highlighted. One is this kind of strange long-range connection. Even though it doesn't allow you to send information faster than the speed of light, there's still this long-range quality. And also, Einstein resisted objects, particles, not having definite features before they're measured. So he had this notion that perhaps there were hidden variables, there were hidden qualities of the particles, even though quantum mechanics could only tell you that the spin, say, of a particle could be up or could be down, Einstein would say, no, no, no. Intrinsically, it is either up or down, and it's just that quantum mechanics is unable to tell us which. And so, what would you tell Einstein today on how to think about those issues?
I wish I could have a conversation. I wouldn't maybe start it that way.
Well, we'll have avatars soon.
Not with you got the quantum mechanics thing wrong. But I would tell him that he was asking the right questions, and that it was good that he wasn't content with just making declarations about how the universe should be. There's a philosopher down at NYU who likes to make declarations like this a lot. And it's like the universe has to be the way that I declare. And if I'm not happy, then there's something wrong with this theory that explains all the data. And Einstein wasn't lazy. He was willing to try and push it further, to try and really sharpen the discomfort he had as much as possible. And he may have felt that he sharpened it into a real paradox. This is what we're supposed to do as physicists, right? We're supposed to sort of make it as clear as possible what the critical sort of things are that are conflicting with each other, or why am I not liking this? Well, let's make it completely clean. Like, what would it imply that I just cannot bear? And so that's, I think, why he wrote this paper with Podolsky and Rosen on this spooky action at a distance, on what we now call entanglement. Now, we now know that this is just a thing. It's real. We can check it. It's there, and it's just true. But it is, in a way, what's most interesting about quantum mechanics. So this discomfort usually forces us to go into places where the theories that we have are the most interesting, where they give us the most new information about how nature works.
Yeah.
And so I would compliment him on that. And I mean, not bad for a 50-something-year-old.
Yeah, right, absolutely. So let's hold quantum mechanics on the side then for a moment. We're going to come back to it, of course, but let's turn to the other big idea, and of course it's also an Einsteinian development, which is the general theory of relativity, a subject that you've spent a lot of time thinking about and working on. And so you mentioned in response to my first question that unlike quantum mechanics, general relativity does seem to give rise to evidence suggesting that it's not a complete theory.
Yeah.
And among the things that you mentioned were singularities, and of course a singularity is inherent to a solution that Karl Schwarzschild gave us back in 1916, the black hole solution. So maybe just give us a sense of, again, I think our audience is largely familiar with that solution. Just say a few words about it, and then what actually do we mean by a singularity when we're talking about in the context of a black hole?
I want to preface this with just maybe a brief remark on this singularity isn't the only reason that we think general relativity is incomplete or needs some kind of completion modification. Another is that the exact same reason why we needed quantum mechanics, the fact that otherwise warm bodies would radiate an infinite amount of power, applies to general relativity as well. If you leave it as a classical theory, then anything would just radiate an infinite amount of gravitational waves. And so it's at several different levels, it's clear that this theory cannot be completely correct. What Schwarzschild did was he found, this seemed kind of important, he found a solution that was like, what is the gravitational field of a point-like mass? And in Newtonian gravity, you get to consider this concept of a point-like mass. You can kind of pretend that all of the sun is like located in one point with the same amount of mass, and it wouldn't make the slightest difference to how the Earth moves around it. This is still true up to the last thing I said is still true in general relativity. If we compressed the sun more and more, this wouldn't really have much of an effect on how our planet moves around it. But as we compress the sun more and more, you find that it doesn't really become a sort of mathematical point mass that just sits there in space and you could sort of look at it and maybe, bounce balls off of it or something. It's what happens is if you make the sun too small, smaller than about a kilometer, then it becomes completely unstable gravitationally, and it collapses into what is called a black hole. And from the outside, a black hole kind of looks like a thing, a kilometer in size, a spherical thing that you can sort of probe. It has various properties, but you can also jump into it, and if you do, you can't come back out. So it's there's an event horizon that separates the black hole interior from the rest of space-time. And so in that sense, you cannot really compress the sun into a point-like object. You can only compress it into something whose radius is proportional to its mass, and it's not zero, therefore. Now, the singularity that we were talking about in Schwarzschild's solution, you encounter it if you were to jump into the black hole, and then you keep going. If this is a very large black hole, by the way, you could keep on going for a very long time. For the sun, you would not go on for a very long time. You'd also have to be very small to enter it in the first place. But then eventually you enter a region of space-time where space itself is sort of collapsing underneath you and getting very small, and eventually everything's sort of curled up on curls whose size approaches zero. And as it approaches zero, that this zero is the singularity. When you can't really talk about a curved space anymore, like we talk about, I don't know, an undulating landscape or something, but everything is sort of breaking down, and you don't have a good description anymore.
And mathematically, as you made reference to before, it really is the case that if you push the equations to their limit, you find a number like infinity that pops out. For instance, if you calculate so-called a curvature invariant.
Yeah, exactly.
And so that's a pretty
that
strong...
infinity is basically just the inverse of this radius.
Yes.
Over which the space is curved.
Right.
When that goes to zero, we say that the curvature blows up. It becomes infinite.
And so Einstein, again, enormous credit for all of these profound fundamental ideas, but he resisted the notion of the black hole solution. It wasn't called that back then. But I think in papers as late as the 30s and 40s was trying to suggest that, sure, there's this mathematical solution that you can write down, but it could never be relevant to reality.
Yeah, I'm not a historian of science. My impression is that there were two developments that were really critical for taking black holes in their interior more seriously. One was a paper by Oppenheimer, better known for blowing things up, and Snyder, who I think was a student. They were both at UC Berkeley at the time. I think it was 1939, where they showed they modeled a star that has burnt out of it's run out of fuel, and so there's no heat keeping it keeping it from collapsing under its own gravity. And they modeled this by just saying, well, let's assume it's all dust and there's really no pressure at all. And that was a pretty good model, actually. And they showed that if they start with a perfectly harmless, boring solution of star that's just kind of static and run out of pressure, run out of fuel, they showed that it collapses very nicely, and that from the outside this looks like a black hole of the kind that Schwarzschild had discovered is forming. They also already noticed that the description is very different if you sit on the surface of the star, and that nothing special happens when you cross the event horizon. If you're not paying attention, you can just live your life happily. In fact, we could be entering a really big black hole right now, theoretically, and not notice a thing about it.
Right.
So they already kind of understood that there's a kind of duality of the descriptions with a black hole. It's very different if you're falling in and if you're trying to describe it from far away. But most importantly, they showed that it's not some mathematical construct that's disconnected from reality. They showed that you start with something that is a perfectly harmless, good set of initial conditions, and just let it run, and out comes this thing that Schwarzschild found some 25 years or something earlier. And so I think that was a big step. And another big step was Roger Penrose's work in the 1960s. He found a whole new way of thinking about general relativity that wasn't. People have been trying to find these exact solutions, lots of exact solutions, whether they mean anything or not, whether they have any application or not, wasn't important. And then they didn't even understand these solutions very well because it was hard to understand their causal structure. Like with a black hole, it matters a lot that there's a region that you can enter and not come out of, right? That's much more important than the exact shape and the details and all that stuff. It's where all the interesting physics of the black hole comes from. It's just the fact that you can enter and not get out in the classical theory. Another interesting fact is that it looks like there's a singularity that you eventually encounter. People were really confused about whether this singularity is an artifact of the fact that we just don't know how to do calculations unless we assume a lot of symmetry in order to make our life easier. The intuition is like if you have particles collapsing into each other and they're exactly spherically symmetrically distributed, well, yes, of course, your equations are going to tell you that they sort of form a kind of singular construct that, where there's an infinite amount of mass in zero volume. Sorry, a finite amount of mass in zero volume, so infinite density. But as soon as you let them give the particles a little bit of angular momentum, they're all going to miss each other and go back out, right? That's classically, that's exactly what would happen. And there were arguments that this is what should happen for the kind of thing that Oppenheimer and Snyder studied as well. In fact, there was a couple of Russian scientists who thought they had proven that this is what happens. And so when Penrose came along, he came along with completely new techniques from a branch of mathematics called topology that allowed him to ignore the messy details of gravitational collapse and focus in on just key questions like, does the world end inside a black hole, yes or no? Can particles encounter a situation where after a finite amount of time, there's no space and time left to go to? He invented this kind of criterion as a way of thinking about what a singularity is.
Yep.
And then, which is actually a pretty good criterion, but moreover, it's one where where you are able to prove that no, it doesn't help if you give that dust a little bit of a spin. It doesn't matter at all. You can show that there are sufficient conditions that guarantee that a singularity will form, and you can check that those sufficient conditions hold in a place where it's very easy to do the math. And so that was, I think, another big breakthrough in forcing people to, I wasn't around, but I imagine that if you wanted to not take the interior of a black hole and the singularity seriously, you could have gotten away with that until Penrose's work.
Right. Yeah, and the lore of that work is what drew me as a beginning graduate student to join Penrose's group at Oxford. That's sort of where but unfortunately at that point he had moved on to other ideas that were less compelling to me, so I crossed the street and went over to the physics department. But so that was at Oxford. Now your advisor was Stephen Hawking at Cambridge, yes. Right? So we were students of both at some level, these titans of the field. And of course, Stephen Hawking spent a lot of time and had a profound impact on our understanding of black holes, which kind of brings the two parts of our conversation begin to sort of come together as he began to wonder about a blending of general relativity and quantum mechanics that would give him some insight into qualities of a black hole that people like Jacob Bekenstein and John Wheeler had begun to think about. So can you just give a quick summary of the insights into what we now call Hawking radiation and sort of how Hawking came to these ideas?
I again, obviously I wasn't around, but the story that I've heard consistently from the major players, including Hawking, Bekenstein, and others, was that this was really discovered through two different paths. The fact that black holes radiate. One path kind of almost got there. It was Jacob Bekenstein worrying about deep questions about thermodynamics in the presence of black holes. There's this thing called entropy. It measures how much we don't know about a quantum system, how many different states it could be in, given what little we know about it. And this, the entropy tends to go up. This is what the famous second law of thermodynamics says. It doesn't have to go up, but it will go up with overwhelming probability in most physical processes. And Bekenstein was asked, by his advisor John Wheeler, to worry about the question of, well, can't we just undermine the second law of thermodynamics by throwing stuff into a black hole, and then for all practical purposes it's gone.
He liked to throw a hot teacup.
A hot teacup, yeah. He wasn't even British, but there you go. That probably paved the way for the British physicists to enter the field. It's a little bit more subtle. You have to know enough general relativity to know that if you throw the hot teacup in, you cannot go and check that its entropy is still there, even if you jump into the black hole later on, unless you jump like immediately right after the teacup. But a very short time afterwards, there is no way for you to access this teacup anymore, because roughly speaking, you get to a different part of the singularity than the teacup, and you can't catch up with it. You're both already kind of at the end of space-time in different places, and they were worried about this problem, and it was a back and forth. Bekenstein realized that this has to be resolved in the same way that we resolve the paradox of what if you put the teacup in the fridge? The teacup gets colder, its entropy goes down. Oh my goodness, the second law of thermodynamics is violated. We should all jump off a cliff. But no, in fact, the fridge heats the room as it's cooling the teacup, and you find that it creates far more entropy than what is lost in the teacup. And Bekenstein figured something like this has to be going on. The teacup's really gone, but some other entropy must have increased. Which other entropy? Well, if you throw a teacup into a black hole, what will happen is the black hole gets bigger. Okay, so maybe we should associate entropy to a black hole. And conveniently, Hawking, a year earlier, we're talking 1972 for Bekenstein, 71 for Hawking, he had proven something called the area theorem for black holes, which showed that assuming that matter isn't completely crazily weird, that the area of the black hole event horizon, this sort of sphere of no return or surface of no return, cannot decrease in any physical process. Unlike with the second law of thermodynamics, this wasn't a statistical statement, it was a mathematical theorem in general relativity. And of course, Bekenstein looked at that and said, oh, I've got my candidate for the entropy. Because how many things have this property that they can't go down? How about I just say it's the area? It could have been some power of the area, but that was the simplest. Proposal. Now he needed to convert, entropy is basically just a number, so he needed to say area in some units. There's some basic units you can build out of the constants of nature that have the same dimension as area. They're called the Planck area, and it's really small. It's 10 to the minus 33 centimeters on each side, square, really tiny. Ask how many squares like that fit onto the horizon surface of a black hole. Bekenstein didn't know, maybe up to a factor of 2, 4, pi, something like that. But roughly that's what the entropy of a black hole should be. And when I throw in the teacup, the black hole gets larger. This is a guess he made, that the black hole always gets larger by enough to make up for the lost entropy of the teacup. But that was his guess.
Right.
Okay, so he proposed that black holes have an entropy, meaning there's a number of quantum states, e to the entropy, exponential in this entropy, that can be associated to a black hole. We'll have to come back to just how radical of a statement that was. But what he didn't do, and it's one of those amazing, funny misses in the history of physics, is to say, well, I know what the mass of a black hole is. I know now presumably what its entropy is, then I can use something called the first law of thermodynamics to compute its temperature. Temperature?
Yeah.
So that was a bridge too far. I asked him about this later, and I was like, yeah, it would have been...
Was because he wasn't taking the entropy seriously as an entropy?
He'd already gone out there on a limb, and he was being, this is the other irony, Hawking said, this is silly. This can't be right.
Right.
Because if it was right, then black holes would have to radiate. That was literally what Hawking criticized Bekenstein for when Bekenstein proposed this. Hawking was probably a little bit annoyed because he'd been writing all sorts of papers pointing out the parallels between the laws of thermodynamics and certain dynamical laws of black holes, showing that there's nice analogs, but refusing to take those analogs seriously because then black holes would have to radiate. So, we see this over and over. The giants get things wrong sometimes. Sometimes it's too much to accept, and you're just dragged kicking and screaming sooner or later to that conclusion that you initially rejected. For Hawking, it happened because he did what seemed like a completely different calculation. He wanted to understand whether rotating black holes, which sometimes can give energy off to the environment, how they do this when we treat the matter outside the black hole using quantum mechanics. It seemed like an innocent enough problem. That's a straightforward calculation. But then he realized that even if they don't rotate, they still seem to be giving off energy to the environment, and it looks exactly like they're radiating with a certain temperature. And whoops, it's kind of the temperature that would have come out of Bekenstein's guess about entropy. Except that Hawking got all the factors of 2 and pi and everything right, so then you could work backwards and fix the factors in Bekenstein's proposal, and now we know exactly what the entropy of a black hole is. It's the area divided by 4 times these funny tiles.
Right.
So that was probably still a abridged version of the convoluted story of how that discovery was made. But I want to say what I feel like was not appreciated until much later about this discovery. Everybody was emphasizing the shocking fact that black holes radiate at all. Classically, they can't radiate. But let's remember the famous, ultraviolet catastrophe that led, I referred to it earlier when we talked about how gravity needs to be quantized, that led to quantum mechanics in the first place. Classically, nothing can radiate. Everything should be at 0 temperature because to heat it up at all would take an infinite amount of energy.
Yep.
So it should not have come as a complete shock that when you treat black holes quantum mechanically, that they do radiate. I mean, it's not like, okay, I don't mean to minimize the fact you can count, but what's really shocking, and what has no parallel that I can think of in any other part of physics, is the following thing. So when we talk about entropy, we now know that we're talking about the number of quantum states a system can be in, given certain macroscopic features we know about it. The exponential of the entropy is roughly that number of states. But entropy is actually a 19th century concept that predates quantum mechanics. And it was invented as a sort of convenient way of keeping track of certain quantities in thermodynamics. The way that people measured it without knowing what quantum states are is, if you have a crystal, for example, from, a block of iron, and what you can do is you can measure how much energy you have to put in to heat it up by 1 degree. And that amount of energy you have to put in per degree of increased temperature, that's basically the difference in entropy before and after I heated it up by 1 degree. And so that's one way in which you can know what the entropy of an object is. You can have it in your lab and heat it up or cool it down or whatever. See how much energy comes out when you cool it down. Another way that we know how much entropy something has is if you tell me what its quantum structure is. You tell me all the ways it can wiggle, and then I can just calculate that number of ways it can wiggle, and that's basically the number of states.
Just count the number.
Just count it, exactly. And that's it. Those are the 2 ways that you are supposed to be able to find out what the entropy of something is. Now, for a black hole, Hawking had neither of those things. He didn't have one in his lab that he could heat up or cool down. And certainly to this day, we don't understand what the quantum states of most black holes actually are. And yet we have a very high degree of confidence that we know how many quantum states it has. This is absolutely unprecedented. It should have blown people's minds. And this is why I go around telling people that gravity is smarter than you. Gravity knows stuff that it has no right to know. It knows about its own quantum states, even though it's this like innocuous classical theory.
In fact, that was my next question. So you've read my mind, or we just are heading along tracks that are converging. How is it that gravity can do this, right? It's astounding,
yeah.
Right?
I think that by now we know that gravity is at some level already
Quantum mechanical.
And that's why it's so different from all the other theories.
Yeah.
That's why also when you try to quantize it, the way we quantized electromagnetic fields, for example, there's a certain crank you can turn. You can start with your classical theory. I mean, there's some choices you have to make, but basically, you start making them more quantum, and out comes a nice quantum theory. And that's what people tried to do in the 70s, and it blew up in their faces. Yep. And in hindsight, I think there are two reasons for that. Gravity is already quantum. It already knows, it has quantum mechanics already built into it secretly. And it also tells you that there are far fewer ways that ordinary matter can wiggle than what we naively think. It tells you that the universe is holographic, that the amount of information in it scales not with the volume of regions, but only with their surface area. So if I double each side of a cube, I only can fit 4 times as much information, not 8 times in it.
And so the information in some sense is residing on the surface in some deep sense?
Yes, and in the last 25 or more years, this has become very concrete through something called the ADS-CFT correspondence, where at least in one class of universes, this is almost literally what is happening. We have a complete quantum gravity theory that resides on a surface that you can think of as a very, very large sphere surrounding the universe, and you can explicitly check that the amount of information scales in the way that I've just described. And I want to come back to Bekenstein and his idea that giving black holes an entropy, saying that they have an entropy, resolves this problem with the second law of thermodynamics. It's all there in these early discoveries. Gravity knows about its own quantum states because we can apparently calculate what the entropy of a black hole is. This idea that the second law still works when I throw the teacup into the black hole tells us immediately that it must also know something about the quantum states of matter. Even though we even don't know what the smallest constituents are, quarks, strings, I don't know. Why is this? Well, when I throw a teacup into a black hole, and I believe Bekenstein that the black hole entropy increases by more than the teacup entropy that I've destroyed, well, what governs the increase of the black hole entropy? It's seemingly the behavior of a classical theory that only cares about things like the mass and the size of the teacup. I can calculate how much the area goes up, knowing only those crude quantities. But yet, every time you try, one example, another example, you find, oh, it works. Now, the area always goes up by enough. You can kind of make it close to not working by throwing in only one particle and very carefully and first lowering it towards the black hole, but it still works.
Right.
And it seems like a conspiracy. It tells us that there's something gravity knows about the universe that, we don't even, this would be true if I throw an arbitrary object that I don't even know what its composition is into a black hole. And I'm guaranteed that its entropy was less than what the area increased by. So gravity can tell me an upper bound on the entropy of matter. And this is what sort of led to the holographic principle, the idea that the maximum amount of information you can have in a region of space is governed by the area of surfaces that surround that region. If you had more information than a black hole with the same surface, well, it seems like it could violate the second law of thermodynamics by converting the region into a black hole of the same size, and thereby decreasing the entropy. And so that's where holographic entropy bounds started. And these statements that I just made are actually a bit wrong, because you can have regions of space that you cannot convert into a black hole because they're expanding or collapsing too quickly.
Or just have it rush by and Lorentz contract.
Exactly. It's also true that I can surround the room that we sit in, bizarrely, with arbitrarily small area surfaces because of the funny way that Lorentz contraction works.
But then you find a way of making this all work.
And then I found a way of making it all work, and it really goes far beyond just the original setting of black holes, where we first saw this pattern. It still, comes across as a conspiracy. It's a statement that you pick any area you like. There's a region I can construct. It's called the light sheet region away from that area. And you just check it every time. The amount of entropy in that region is going to be less than that area. In simple
Even
examples,
in all the examples that you could put forward to break the more conventional framework, in your approach, all of those examples are covered.
That's right. Yeah, if you surround this room with one of these funny areas that have, surfaces that have almost zero area, you find that the light sheets don't actually see the room, and so on. So it's completely general. It applies to arbitrary universes and so on.
And so what is the whole holographic framework telling us? Because normally our intuition, and certainly 18th century, 19th century, or 20th century physics, still, even with the entanglement of quantum mechanics, the view was, if you want to count the number of configurations, states within any volume, it's got to be proportional to the volume, because you can change the state of the system at every location within that volume. So if you double the volume, you've got to double the number of things that you can change. You've doubled the number of states. But as you're pointing out, if it's more in area, just in sort of the more conventional framework that's easier to describe, it doesn't scale as the volume, it scales at the area. So what's that telling us about the independence of the locations within a volume?
Yeah, it tells us that there is something fundamentally non-local about quantum gravity. That, it's certainly true that I can use, if I had a grid of, particles each in a little cube, I can flip this one, or I can flip that one, or I can flip this one. But if I try to play with too many of them at the same time, it turns out, and this is sort of the conspiracy, this is the miracle, it turns out that this is always associated with putting enough energy into the system that at the point where I would be violating the holographic entropy bound, or my bound, I would have already made a black hole. I would have put so much mass into this room that it would have collapsed into a black hole, and so that would have frustrated my attempts to max out the amount of entropy that naively we think we get to store in this room using this sort of local intuition. And so what's really happening is not that there are specific cubes that I can't address. I can flip the spin or whatever I'm doing to store information in any one of them, or in any million of them, right? But it's just that if I try to use too many at the same time, so that means that there's something non-local that's preventing me from using this, and it's really gravity at the heart of it. Gravity knows everything. It's the one force that couples to everything. You can't. If that wasn't true, these kinds of ideas would have no chance. It's the universality of gravity that prevents you, for example, from just using some material that doesn't feel gravity, right? Then you could clearly do this. So I feel like gravity has been at the core of almost all the major scientific revolutions. Secretly, already when the ancients observed the planets and came up with a pretty good theory for it, and at the beginning of the modern scientific revolution with Galileo and Newton. So gravity is always lurking there. And it seemed for a while like when quantum mechanics came along that that for once had nothing to do with gravity. And now we're realizing, no.
Yeah, right, exactly. Well, it's a funny thing, because as well, when I would describe string theory, and I think many of us would have used the same language in the 80s and 90s, before holography really took hold the way it did mid-90s or 1997 with Juan Maldacena and the ADS-CFT correspondence and so forth. Certainly the language was always, you've got general relativity on the one hand, you've got quantum mechanics on the other hand, the laws of the big, the laws of the small, and you want to somehow put them together into some unified package. You've got to blend them. And that certainly seems a little bit naive in retrospect, because it's more like you've got quantum mechanics, you've got this thing called gravity that kind of already has some linkage to quantum mechanics, and rather than smashing them together, it's a matter of teasing out how quantum mechanics is within the gravitational structure. Is that a language that you would prefer that we use in describing the charge of trying to get a unified theory?
It certainly describes well what I spend most of my time on. That doesn't mean that everybody should spend all their time on one avenue, right? So I think string theory has certainly shown that it's a very fruitful approach, but it's also a very unconventional and unprecedented approach. We normally start with sort of phenomena we see and try to discern patterns in them and maybe come up with some principle, like the holographic principle and so on. And it's rare, or maybe unprecedented, that some theory falls into our laps that we don't really completely understand, but it has so much structure in it that you can kind of explore it systematically and kind of hope to make contact with the real world. Eventually, because it's so unprecedented, I think it's also a risky approach. And there's sort of the part of my personality that's kind of I wrote a paper with Joe Polchinski sort of saying that we kind of got it wrong about how we were trying to connect string theory with the universe we see. But that doesn't make it, so for example, the ADS-CFT correspondence came out of studying string theory. In hindsight, it didn't have to,
right,
but it came out of that, and it's an incredibly powerful tool that we use all the time, and it helps us weed out so many bad ideas, learn so much about how black holes behave, because they kind of behave the same way in anti-de Sitter space, presumably, as anywhere else. So it doesn't matter for many questions that it's the wrong space-time. So it's great. But the reason that I work on trying to tease out what else gravity knows about quantum mechanics, I think is not just because of my early experience with sort of coming up with this holographic entropy bound, but because I think the field has taken leaps where it's become so precise that it's a discovery tool. We have literally discovered new results about quantum field theory that are really very simple, elegant, but nobody had thought of them before, and they take 100 pages to prove in quantum field theory. And we discovered them by thinking about what might gravity know. And this is, it's a little bit hard to explain what a technical leap this was, but one way of putting it is maybe that, with these entropy bounds, like, how much entropy can you put into this room before it becomes a black hole? It's actually not nearly the surface area. If we really try to do this, it becomes a black hole long before it even reaches the bounds that that you can sort of intuit from black hole thermodynamics. And so it's not a very, it's still stunning that the amount of information scales with the area and not with the volume, but it's a bit of a blunt tool in terms of actually describing how much information there might be in the room. And about 10 years ago, in 2015, Aaron Wall and I and some collaborators were able to condense this to a statement that's much more sort of on the surface of what gravity really allows, connecting directly with what can actually be done with matter. This statement is called the quantum focusing conjecture, and it's in some ways even dumber than the entropy bounds. It's even simpler. It has to do with the fact, everybody's heard about light getting deflected by the sun. That was one of those very famous early experiments to see that general relativity is correct. And you can think of that as focusing, like if you have a bunch of parallel light rays that graze the sun, initially they sort of form a disk, and then when they come out on the other side, the disk will be a little bit smaller. And this is something you can prove will always happen. They don't do the opposite thing. Assuming something called the null energy condition, it just says that the energy density of matter is not negative as seen by light rays.
Right.
Okay. That's a perfectly reasonable condition for the stuff that's around in this room, but it's actually false. And you can make locally negative energy density, and you can really make light rays go like this, start out parallel and then diverge. And it bothered us that we didn't have a way of correcting for that. There was a similar story with Hawking's area theorem, which was wrong for the same reason, the null energy condition doesn't hold, but which then got replaced by the generalized second law that Bekenstein had proposed, which could have been called a quantum-corrected area theorem. So we sought out a quantum-corrected focusing theorem, and we did literally the dumbest thing you can do. You just do the same thing that Bekenstein did. Take the area of a black hole and add the entropy of everything outside to it, and think of that as the quantity you should worry about. This is called the generalized entropy. In this case, it's not the area of a black hole, but the area of the disk that these light rays span. That was kind of the leap. And we said, well, that's the thing that should focus. It should start getting smaller after the light rays have passed an object, even if that object happened to be one of those weird negative energy fluctuations. And by just positing that, we found that, first of all, my bound that I was so proud of just comes out immediately as a consequence. But also the generalized second law comes out as a consequence. Well, that's actually a consequence of my bound. So these were sort of increasingly stronger statements. They were simpler in some sense, but they were also stronger. They implied everything we knew before, but then they also implied something new. They implied something that didn't even have Newton's constant of gravity in it. When you look at the formula, there's only Planck's constant. So it's a statement just about quantum mechanics, or in this case, quantum field theory, the stuff that like the standard model of particle physics that describes all the matter we know. And it was a statement that said that there is, in fact, a lower bound on the energy density at a point. It can be negative. In fact, it can be as negative as you like. But it cannot be more negative than a certain quantity that has to do with how much quantum information you would acquire if you sort of cross that point. And this is a gross oversimplification. It's really the acceleration of the quantum information. It's like a second derivative for those who like math. But the key point is it's a fairly simple quantum information theoretic quantity that gives you this lower bound. And now, because this formula called the quantum null energy condition doesn't have Newton's constant in it, and because we basically completely understand quantum field theory, we got to work and said, well, let's go try and prove that. And we tried to prove it only for certain quantum field theories which are called free, like things don't even talk to each other, which is the simplest thing by far you can try to do, and it still was pretty hard. And I don't know, it was like 25 pages of pretty intense algebra. And then other people came along. Aaron Wall and Tom Faulkner and others had beautiful ideas for how to prove it for the general case, a theory like the actual standard model of particle physics. And you had to really throw the kitchen sink at it. There's all sorts of modular theory and algebraic quantum field theory that I thought I'd never have to learn. And 75 pages later, you get the result. So that for me was completely transformative, because before that, you could have equivocated. It's like, oh, well, yeah, it's cool that gravity kind of knows some stuff and we can roughly check it, but it's never that close anyway, right? So it's more of a conceptual thing, how deep that everything scales with the area and not with the volume. It is pretty deep. But now it's, no, gravity really knows the details. It knows, the stuff after the decimal points. It has an incredibly precise knowledge of how quantum mechanics and quantum field theory must work to be consistent with, fairly straightforward guesses about slight quantum generalizations of gravity,
right.
The guess that we made. And that changes everything. Now it's like, wait a minute, this thing is like an oracle. You just have to ask nicely and it will tell you stuff. Sometimes it will tell you stuff you didn't know. And if we have time, I'd like to give you two more examples of that are
please.
very recent, because I feel like, especially the last 5 years, this has really exploded. One is the famous, triumph, and really it was a triumph of string theory in the 1990s when Strominger and Waffa for the first time were able to count how many states a certain, very special kind of black hole, admittedly, has. These black holes they're supersymmetric. They have, even at zero temperature, they have a lot of possible states they could be in. And using all the tools that had just been discovered in string theory, D-branes, dualities, it's a real tour de force. And then still, having to guess some things. Oh, something called an index is the same as the number of states. Oh, strong and weak coupling, there's no phase transition. You had to put a few guesses in, perfectly reasonable. And then you could do this very amazing calculation and you get exactly the number of states you expected.
All the terms.
And you get the exact integer of states. Yeah. So it's not just e to the area or something, it's like the integer number. And it's a legendary piece of work. Well, just a few years ago, my colleague Luca Iliesiu, who was then not at Berkeley, but I'm very happy he is now, and his collaborators managed to reproduce this result just using gravity, putting it into this sort of formalism of the path integral that we get from quantum mechanics. Normally, that's not a particularly well-defined thing. You can't do arbitrarily exact things when you do this, but in that same setting where you have a lot of supersymmetry, you can perform this calculation exactly. And gravity tells you, if you want to know how many quantum states the black hole has, it basically tells you to sum over all sorts of different geometries that are possible given certain boundary conditions.
And the individual terms, as I recall, they're not even integers.
They're not integers, no. These are ugly things, e to the pi something, blah, blah, blah. And they're complex and whatever they are. Yeah. I mean, it's an absolute mess. Yeah. But it turns out that the mess organizes itself into something called the Rademacher expansion, which came out of analytic number theory. People were interested already like more than 100 years ago in questions like, how many different ways can I write 100 as a sum of positive integers? And that the number of ways grows very, very quickly. It's called the number of partitions of an integer. And there's variants of that are more sophisticated, but that are more or less this kind of question. And starting with this legendary mathematician Ramanujan and his colleague Hardy, people began to come up with approximation schemes for these large integers. Again, this was about 100 years or more ago.
Sure.
And initially, these schemes were not something that would give you an integer, but they quickly became accurate enough that you could just round them and it'd be the right answer. And eventually, and I don't know the history exactly, I guess this guy Rademacher came along and just completed the series. And so he was able to show that this number of partitions, which is by definition, by construction, an integer number, can be written as a sum of infinitely many non-integer terms. And if you hadn't known that you were starting with something that was an integer, you would have been absolutely shocked to see these infinitely many terms and find that they sum up to an integer. What my colleague Luca and his friends did was show that the gravitational path integral gives you these infinitely many terms, and precisely those. Right. Precisely those. And you can sum them up by undoing what Hardy, Ramanujan, and Rademacher did, and you get the integer. And you didn't need D-branes. Yeah. You didn't need any of these things. There was nothing wrong with D-branes, but it's still an assumption. I mean, I don't want to sound heretical, but maybe string theory is wrong. And here it's just gravity.
Right.
And they were able to go beyond these very special black holes somewhat and consider black holes which can also be cooled to zero temperature but aren't supersymmetric. And what does the spectrum look like? And resolve old confusions about whether or not there's a gap in the spectrum and so on. It would get a little too technical to discuss this, but I would like to declare that I thought something like this was impossible, and I'm one of the people who should have been pretty bullish about the gravitational path integral and this sort of way of gravity knowing stuff. Just because to get an integer right, you need infinite precision. Even exponentially good precision is something that I might not have expected gravity to be able to do for us, but you ask the question the right way, and they did, and it does it for us. And then the second recent example
Before
is...
you go into that one, though, just do you want to clarify one point? Because I'm actually very pleased that you said string theory could be wrong, and yet you get this result directly from the gravitational path integral. But to clarify that, I gather what you mean is you don't need string theory to get this out of the gravitational theory. And so string theory could be right, it could be wrong, but
exactly.
this quality...
It's a hypothesis.
Right.
You have to make a hypothesis. There's good reasons why. But even if, and I think maybe that's what you're getting at here, even if string theory is right, and there's certainly, if you asked me, I would find it very unlikely that it doesn't connect with some corner, perhaps a little far from where we are, of the truth. It's always better to have a universal derivation of something. It's always better to have a derivation of an important result that needs fewer hypotheses, fewer assumptions, that tells you what are really the important ingredients and what are just, okay, maybe in this particular way of phrasing it, then it looks like other things are important, but really, it could have never been any other way, and we now know how to do it with very few ingredients.
Right.
Thanks for...
Yeah, and I've little doubt that in the comments, people are going to write at this stage in our conversation, Brian Greene heard the word string theory might be wrong and he jumped all over his guests, which is not the case at all. It should be really clear. I don't care.
I would like to testify that Brian Greene looks perfectly calm right now.
Because I don't care if string theory is right or wrong. I just want us to make advances toward truth, and that's honestly the case. And this is a beautiful example where a result that initially was derived in the context of string theory, as you say, Schrödinger and Vafa used every quality of string theory to just barely pull out this result in a real tour de force approach. And it is remarkable that there are other ways of getting the result that don't need all that architecture and all those features. So that's fantastic. And as you're saying, it just shows how smart gravity is. Intrinsically, it somehow knows more about the world than Einstein would have thought, than we would have thought. So you're going to go on to a second example that sort of takes us further.
So another colleague of mine, Jeff Pennington, as a grad student, turned to the question of, does information come out of a black hole? And this is one of the longest debated questions in the history of science.
Yeah.
It started with Hawking in 1976, pointing out that his calculation of Hawking radiation implies that information is lost. You make a black hole, maybe out of a star in a very definite quantum state. What is supposed to happen if instead the star had just randomly exploded or something, is that if you kept track of everything, which is practically hard, but in principle, we think we could do it, that quantum state would just evolve forward in time. We could later measure it and run it back and know what the star started with. What Hawking showed is that according to his calculation, the black hole just emits garbage. It actually, just coming back to the beginning of our conversation, we were talking about these two qubits that I give one to you, and we both hold garbage because they're entangled.
Yeah.
The reason this is happening is that the black hole gobbles up the star, and then the Hawking radiation comes from a different place altogether. It comes from the horizon of the black hole, which according to general relativity is basically just empty space. And it turns out that when you divide empty space into two halves, the half that's just inside the horizon and the half that's outside, that's a little bit like having these entangled particles. There's excitations of all the fields, like the photon field, for example, that are entangled almost in the way that I described these two qubits, 0, 0, plus 1, 1. And so what the black hole is doing is constantly distributing one half of this pair off to infinity and keeping the other one inside the black hole. And that's why you get no information coming out of the black hole. You get precisely that kind of garbage state, just a lot of it, that we talked about at the very beginning.
In fact, also just to reflect back on the beginning for a split second, according to Hawking's view at that time, this would suggest that there is a crack in quantum mechanics. This would suggest that the information necessary for a quantum mechanical description of the world would not be complete. So I guess that's where Hawking takes his scattering matrix and puts a slash through it and tries to think about the world differently.
Right, and people were up in arms about it. Mostly this apparently fell along the lines of whether you're a particle physicist
or general relativist.
A general relativist.
Yeah.
To a general relativist, this picture that I just described is completely obvious. Like it's not even like the information's really lost, but you just know it's in a place where you can't get to it.
Right.
It's totally obvious. There it is. What's your problem? I just ran into Bob Wald, who's one of my heroes, this morning, and I remember him telling me, like, this makes no sense to even worry about this question. From their perspective, it's just.
So it's just sequestered from their
To a
point of
particle
view.
physicist, this is crazy because they're used to doing these experiments where you smash a bunch of particles together at some accelerator and stuff comes out, and the black hole releases all of its energy back out when it evaporates. So in that sense, everything really comes out. And why should it possibly matter that somewhere in the middle of this process there may or may not have been a black hole? And I think that was sort of the intuition of people who think about particles a lot. And so this debate raged on for about 25 years. And then, let me see if I got the counting about right. Yeah, okay, a little over 20 years. And then this idea of the ADS-CFT correspondence came along, where we could, for the first time, study the formation and evaporation of a black hole in a complete quantum gravity theory. Now, we have to believe that the correspondence is actually correct, but there was pretty overwhelming evidence for it. And then the calculation is pretty easy because the theory that Juan Malacena said is it's the quantum theory that describes this universe in which you formed a black hole and let it evaporate. That theory is just a standard quantum mechanical theory.
A thermal at a temperature.
Yeah. Independently of the details, the way that it would evolve from the time when you had a bunch of particles very far out, sort of near infinity, that you sent in, to the later time when all those particles come out as Hawking radiation, or the new particles come out as Hawking radiation, it just looks like ordinary quantum evolution. It has no chance of losing information. Right. It can't. So again, this was very powerful, and I think it convinced a lot of people, including Stephen, that information does come out. But I think people quickly forgot about the price for information coming out. The price is high because Hawking didn't make a mistake. He didn't make some crazy assumption that we can easily give up, and now his calculation is wrong, and it's clear why the information can come out. He wasn't assuming much more than that the horizon of a black hole is what general relativity says it is. It's empty space. And how could it not be empty space? You're at the horizon of a black hole. Anything you try to put there is going to fall in right away, and then it's going to be empty space again. So it seemed like a totally innocuous assumption. And another several years later, in 2012, Joe Polchinski and his collaborators wrote what we usually call the AMPS paper after their initials, or the firewall paper, where they basically just ran the argument backward. You want to have your information come out? Be my guest. Here's the price. Here's what you're going to have at the horizon of a black hole. You rescued quantum mechanics, but general relativity is completely wrong. Right. So this is what we love. We love to have these very sharp paradoxes, and I think this is this is certainly a paradox I'm still enthusiastically working on, and I feel like we've not resolved it, and it's a big opportunity for progress. But I wanted to not emphasize that so much. I wanted to emphasize work by Jeff Pennington in 2019, and also by another group, Almeri, Engelhardt, Maroff, and Maxfield, who used the oracle. Again, no ADS-CFT correspondence, no assumption that works, they just asked the gravity oracle. Please, oracle, tell me, what is the entropy of the Hawking radiation that comes out of a black hole? Now, the important thing is to emphasize that this is not exactly the same question that Stephen Hawking asked. Stephen Hawking asked, what is the quantum state of the Hawking radiation that comes out of a black hole? And this is a very sort of big, it's like a big matrix, each, of dimension, e to the area times e to the area. It's a gigantic bunch of numbers. And his calculation showed that this matrix is sort of the garbage state, the state where this radiation contains no information at all. But it's a very complicated object he was computing. What these two collaborations figured out is how to ask the oracle directly. Well, no, just tell me one number. Tell me what is the entropy of the radiation. Now, if Hawking was right, and you keep getting more and more garbage as the black hole gets smaller, the entropy has to go up. It just keeps going up, 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 and then when the black hole's gone, it stays there, and you've got this like, the fact that the entropy is so large is a restatement of the fact that you got garbage out. For a black hole that returns information, you don't expect that it returns it all of a sudden or something. What you expect is what should happen for any other system where you're slowly getting access to more and more of the system. Think of the radiation coming out as we're getting access to more and more of what is ultimately all of the radiation cloud into which the black hole has turned itself. And what should then happen, and this is just a very general result in quantum mechanics, is the entropy should first go up, and then it should go down back all the way to zero, and the fact that it goes down to zero tells you all the information has come out. E to the 0 is 1. There's only one possible state.
So as that Don Page had
and
originally
that's
shown
called
us,
the Page curve. That's, it was characterized by Page as sort of the thing you'd have to show if you wanted to show at the level of entropy that information comes out. And what they did was they realized that we actually have a way of directly asking gravity what the entropy is. This is through something called the quantum extremal surface prescription, which Neda Engelhardt, one of the collaborators in one of these papers, was actually instrumental with Aaron Wall in coming up with that. It's a certain way of looking at the geometry, finding special surfaces, and these surfaces tell you about an entropy. This can be understood as sort of asking the oracle, because as Lukowitz and Malasena showed, this isn't just some silly rule somebody came up with and pulled out of a hat. Actually, it was pulled out of a hat initially. But the reason it works is that it can be thought of as the answer that gravity would give you to a certain question of like, I would like to compute the entropy in this and that particular way. You compute a bunch of things called Renyi entropies, and then you do some mathematical trick called analytic continuation. And this thing they pulled out of the hat initially is just a shortcut for that procedure. So that procedure is really, I'm asking gravity to compute the entropy for me. And that's what they did, and they got the Page curve. And this was it was a landmark result, absolutely stunning, and no extra assumptions needed. Now, we can talk about the apparent contradiction between Hawking using the same framework to say information is lost and them using that framework to say it comes out. But for the time being, I just want to make the point that these aren't small technical results. These are answers to what we have long considered some of the deepest questions in physics. And gravity knows these answers. It's incredible.
Right. And so is there a larger lesson that we can take away from this now? I mean, it's maybe too early in the maturation of these ideas, but in some sense, are we learning that we just need to probe the depths of gravity, and that's the most fruitful way to get to some complete description?
I'm certainly, I am of the opinion that we need a strong, concerted effort to turn this into, how can I just phrase the question right? What might be possible? I don't know. It's a bit of a dark art right now. It's very sort of, you have to come up with things that you might ask gravity in the right way, and then does these amazing things for you. We need to do better than that. I mean, you cannot have something as powerful right in front of your nose and not understand why it works, how it works, how far you can push it, how many more things you can ask it. It's already given us things we didn't know. So I'm not saying that somehow classical gravity is already the final theory.
Right.
It's just that we have yet to find what it can't tell us about this final theory if we just ask the right question, if we just go about it right. And so we need to find out, we need to make this more systematic. We can't have this be done by magicians. This has to become, doable by the masses, if you will, so that we can systematically exploit and learn from this amazing oracle. Gravity is very sophisticated. I think you had Daniel Harlow in one of these conversations recently, and I'm sure you talked about quantum error correction.
We did.
Gravity uses quantum error correction.
Yeah, that's...
It thinks like an engineer.
Yeah.
Another example is...
So what do you make of that? I mean, I find that utterly stunning, that the way we do quantum error correction, completely not thinking about gravitational ideas, is somehow the way we can encode boundary states versus bulk states. Why? I mean...
Well, yeah, why? I mean, this, I'm sure Daniel explained this very well, and I'll refer to him. This started out as a way to sort of deal with apparent paradoxes in the ADS-CFT correspondence. But I want to emphasize the sort of real world. I mean, one take on this is that quantum error correction is maybe much deeper than. It certainly is much deeper than when I first heard about it. I was like, okay, let people work on this, like how to fix their crappy quantum computers.
Exactly.
It's an engineering problem. How important can it be? Right. I say this with deep regret because I was just being a dumb graduate student who had just watched John Freskel, switch to that field. And I'm like, why doesn't he want to work on black holes anymore? Turns out he was working on black holes all along, just smarter than I was.
Well, but he certainly didn't know that
He did not know that at the time, but give him credit.
Sure.
This is what he decided to work on, having just spent several years thinking deeply about black holes. I don't know, I've never really asked him directly.
That's just coincidence, right?
Yeah, it's probably just coincidence, I mean, it's...
All right, we're going to have him on. I'm going to ask him this question.
You should ask him about that.
He taught me classical mechanics when I was an undergraduate.
There were so many times I was like, I'll never have to learn algebraic quantum field theory. I was pretty sure I'd never have to learn about quantum error correction. It's amazing that gravity thinks like an engineer. And another example is, when we try to understand what part of anti-de Sitter we can actually reconstruct from if we just have part of its boundary. Turns out that's because of this quantum error correction idea that's not nothing. That's actually pretty good. You can construct a very nice amount of the spacetime and sort of know what's going on inside this box. But when you get into the details of how big this region is, it turns out that quantum error correction it's not enough to say that. You have to ask whether gravity can succeed in certain, to me, completely unheard of quantum tasks that colleagues of mine like Jeff Pennington know about because they were trained in quantum information theory. Something called single-shot quantum state merging. I know that's a handful.
Now you've entered a realm that I don't know anything about.
Let me just emphasize the word single-shot here. There's these things called the von Neumann entropy that measure the resources that I would need to send many messages. So for example, when we compress files on the computer, it takes advantage of the fact that it's a big file. It's not like 3 letters. It's a very big file, and maybe it's a text file, and so certain letter sequences will occur much more likely than others, and it gives you a way of compressing it. And so the resource in this case, how much disk space you need for the file, is measured by the von Neumann entropy of the sort of distribution of letters in your message. But then there are also situations where you might just have, you might just need to send 1 letter. And then, you're out of log, you need log to the base 226 bits to encode that 1 letter. There's no good way of compressing it any further because it could be any letter unless you're willing to make errors. This is a very sort of ugly, real-world kind of problem. Nothing idealized about it, not pretty, right? And yet, that's the kind of problem that gravity is solving when it determines how much of a space-time you can describe from the gravitational state. This is something that my former student Chris Akers and Jeff Pennington discovered. So again, it's more like, I would have classified that under engineering problem. Yeah, if I ever come in, it can't possibly rear its head in, the realm of quantum gravity that's so far removed from our everyday concerns.
Yeah.
And yet here it is. So there is so much buried there that we need to get out.
Yeah, it's amazing. If you have time, I wanted to quickly touch on one other subject that you made reference to quickly, work that you did with Joe Polchinski, which again, as you say, sort of radically transformed how people in that era were trying to imagine string theory making connection with the standard model, observable physics. And so maybe you can just give us a quick summary of what you found there, and then we can just sort of bring it up to date in terms of how one thinks about these things.
Right. So Joe and I had both been worrying about what's called the cosmological constant problem. The problem is that when you ask our best theories, quantum field theory, it turns out that empty space not only can have energy, some amount of energy per volume, energy density, but generically has to, unless you have like some high degree of symmetry that we definitely do not have in our universe, called supersymmetry, unbroken. And worse than that, you can estimate the contributions to this energy density from all sorts of different things that are going on in the standard model. Again, a very well-tested theory in every other respect, in detail. You know, all these particles, we've seen them. And they make contributions to the energy density that were known already in the 1970s to be 50, 60 orders of magnitude larger, at least, than what was then known to be the upper bound. It was then not known exactly what the value is, but it was clear that there's a big mismatch. And so by the late 80s, Steve Weinberg and others had, I think, similar ideas, but Steve Weinberg was particularly clear about it, I think. He said that, you know, this is a big problem, and there are, you know, fairly universal reasons why this isn't going to have the kind of solution where, oh, you find some mechanism that makes the cosmological constant want to get small. The reason is that you may know that well, you certainly know, but hopefully your audience too, that in physics usually just energy differences matter. It doesn't matter whether I call, you know, the first floor ground zero, and then when I jump off of it, you know, I hurt my ankles the same way. Whether, you know, what name I give to the heights, I could use above the sea or something. It does, you know, these are conventions. The only thing that matters is how far did I fall, and there's one exception to that. There's only one force that knows about absolute values of energy, and it's gravity. And gravity was completely swamped by other contributions to the energy density for almost the entire history of the universe. What we now know is the value of the cosmological constant. It's, you know, 10 to the minus 123 in certain natural units. Well, there's no way that gravity could try to aim for that. Yeah. Gravity is the only thing they could have aimed in the first place, and it could only aim for that if you first get rid of all the other matter. That's what's called the empty universe problem with attractor mechanisms for the cosmological constant to get small. You first have to empty out the whole universe, and then gravity can implement whatever your favorite, you know, feedback mechanism is by which the thing eventually gets smaller and goes close to zero, or maybe even to zero. Weinberg understood that this is a fundamental obstruction. You will never have a theory that does this and connects with cosmology, not even close. You know, you have to solve the problem in the real universe, not in some fake universe. And so he said, no, this is going to have to be an environmental selection principle, meaning it's going to be something like, you know, Kepler had this idea of a fourth law. I mean, he was on a roll with the first
to determine
where
are
the planets, you know, the spacing. It must also be, it's crystals and how they're not crystals, like platonic solids and how they fit in. It was a fair, you know, it was a reasonable thing to try. You don't know ahead of time in physics what is done, what is an outcome that happened by chance, and what is a truly fundamental thing. Today we know it's a bunch of mess that collapsed to form one solar system among a gazillion, and they're all different. And many of them don't have Earth-like planets, probably, right? So it's not a miracle that we are on one where there's water and, you know, interesting physics can happen, interesting chemistry can happen. That's where we find ourselves because, you know, here we are, we're complicated things for which you need interesting chemistry to happen. And so Weinberg's idea was that the cosmological constant would be in that category and not in the platonic solids category. And what happened afterwards was that it turned out to be surprisingly difficult to implement his idea. First of all, there weren't really any theories that naturally gave you many different possible values of the cosmological constant. And if you forced it by just adding some potential for some field that could like rest in many different, like go down tiny little steps, then you ended up back with this empty universe problem. And when we first talked about this, it was actually completely by chance. I was just passing through Santa Barbara. I walked into Joe's office. What have you been thinking about? Oh, the cosmological constant problem. Well, I think I know how to solve this part. And oh, I think I know how to solve the other part. And so we started talking. It turns out that string theory is tailor-made for this. Yeah. Through something that was often used by critics of string theory as an argument against it. Oh, it has all these extra dimensions. Why don't we live in 10 dimensions? No, you have to contort yourself to get down to, to 3 plus 1 for time. And, it's like it's not wanting, So it turns out that there's many more ways. It also bothered people that there's several different ways of getting down from 10 dimensions to 3 by making the others really small, so-called compactifications. What Joe and I pointed out is that there are actually far more compactifications, thanks to these objects D-branes that he had invented, that should be possible, and that the number is easily astronomical. This shouldn't shock you as much as it shocks people. I mean, it's just like saying that if I have like the electron and the quarks and the photon, I can build atoms. Out of these atoms, I can build like a gazillion different objects. I mean, there's a far larger number of different matter objects I can build than the number we were quoting here. But we pointed out that there's easily enough ways of making three-dimensional space for some of them to have a very small cosmological constant just by accidental cancellations between the different contributions from all sorts of pieces of the particles that are around and the forces that are around. And we pointed out that the way that this is structured is sort of very chaotic, that it's not true that if I change some ingredient in how our vacuum was made, our empty space was made, to sort of the next one over, that the cosmological constant should be similar. And this was important because it meant that as the universe sort of explored all these configurations, and there's a way for it to, this was already known that there's a way for the universe to kind of explore them. It's a bit like a radioactive decay chain where, an atom can decay into like 3 different things and each of those can decay into different things. As the universe explores this, at the point where it finds our way of putting 3 dimensions together, it is typically going to come from some value of the cosmological constant that's just completely random, meaning huge. And that means that you have enough energy around to connect to standard cosmology, which you have to do because we understand it very well. We know it back to at least Big Bang nucleosynthesis, very good accuracy. You have to make a hot Big Bang. The hot Big Bang in this picture is really just the decay of a parent vacuum, of a way of tying together the extra dimensions, and something snaps a little bit, and now you get to our way of tying them together, and this snap releases a lot of energy and heats up the universe. And so what people, initially a lot of string theorists were very opposed to this idea because it didn't just follow Weinberg in putting the cosmological constant into the accidents of our environment category of objects. It put a lot of things. The dream of string theory, perhaps a little unrealistically, was you'd get the electron mass from 2s and pi's. There was never a good, in principle, reason why that should happen, and it was, I think, a little bit delusional given that we knew our universe has so little symmetry.
Well, there was a period of time, like when I was a beginning graduate student, the number of known compactifications was small, and the number that gave rise to 3 generations of particles was smaller still. And so there was a reasonable hope for a small period of time, and I happened to be a graduate student just in that window, that maybe there were just 1 or a small number of compactifications if you put in the most meager amount of particle physics data, like 3 generations of particles.
And it's easy to say later on, look, Bekenstein had to ignore the fact that his proposal absurdly predicted that black holes would radiate. He went ahead anyway. string theorists had to ignore the cosmological constant problem.
Right.
They had to ignore the fact that the standard model just gives you all these contributions, and everything you say about how you're going to get your standard model out of the compactifications you're discussing really makes no sense in that context.
Right.
And that's okay.
Sure.
We have to do that sometimes. We have to ignore inconvenient information, and sometimes that's too bad. We do things that are wrong, but sometimes it's also good, as Bekenstein's example shows, because later the inconvenient information is going to find a way to fit itself into the story. You don't know that at the moment. When you're in the midst of it, you have to follow what looks exciting right now.
Right.
So I don't, but what happened was that this was kind of a nail in the coffin of that idea. I mean, my work with Joe, of that idea that everything would just uniquely come out of string theory.
Yes, exactly.
And it made it more like the way physics has kind of worked in the past. We don't think that we can describe the behavior of a zebra using the standard model of particle physics. That doesn't mean
directly.
That doesn't mean we think there's something happening in the brain of a zebra that violates the standard model of particle physics. It's just not practical.
Right.
There's too big of a difference in sort of energy scales and complexity for this to be a viable proposal, or perhaps more importantly, for zoology to be a useful way to learn about the standard model.
Right.
And in a similar way, I feel like we felt like maybe we wanted to connect the standard model to string theory in a way that's a little bit like connecting the zebra to the standard model.
Right. No, I agree with that.
Yeah.
So one final question before we wrap up, to try to maybe bring these two threads together. So you emphasized the oracle quality of gravity. If you know how to ask it a question, somehow it's able to give you answers that you did not think it should be able to answer.
Yeah.
Do you think the cosmological constant, the dark energy, might be among the questions that the oracle will be able to answer?
That's a great question. I would say no if Joe and I are right, for exactly the same reason. That the kind of questions that have to do with extremely complicated objects, which, again, in this picture, the standard model is like the zebra. It's the accident of, or the outcome of some nebulae collapsing and forming our solar system. It's the outcome of some process that is, about which we will basically never be able to have all of the information. We'll never be able to calculate it more than, statistically. Then again, I've underestimated gravity before. And this really goes back to what I was saying earlier. Independently of whether this particular question is in the scope of what gravity can reach, it's clear that it's immensely more powerful than we had realized. And we need to learn how to harness that power. We need to make this much more systematic, understand what's under the hood, understand who is smoking the drugs, like in the Oracle of Delphi, and what exactly they're doing.
Yeah.
And make the thing automatic. Make it less mysterious.
Yeah.
And it just seems like we have this powerful black box in front of us, and it's time to find out how it works.
Fantastic. Well, look, this has been a rich, fascinating conversation. So thanks so much for spending the time, and
Thank you,
I'm
Brian.
looking forward to the
So
next
much fun.
one.